So we're now going to look at the Gibbs energy for a mixture. And so we have here an equation that shows us that the total Gibbs energy is going to be equal to we have two components, so A and B. And so it's going to equal to the molar Gibbs energy of substance A times the number of moles of substance A plus the molar Gibbs energy of substance B times the number of moles of substance B. And so this molar Gibbs energy is an important enough quantity that we give it its own symbol, the Greek letter mu. And so we're going to call it the chemical potential from now on, but it is the molar Gibbs energy for that substance. And so I've just rewritten the equation using this new symbol. And so we know from before how the molar Gibbs energy depends on the pressure for a gas. And so we're going to rewrite it to determine how the molar Gibbs energy changes for based on the composition of a mixture. And so we're going to use this symbol, which tells us that it's the pressure at 1 bar. And so this is pressure at standard conditions. So that's our 1 bar. And then we have our molar Gibbs energy, which is our Gibbs energy at standard conditions, which is 1 bar. And so it doesn't look that different from what we've seen before, but now we're going to adapt it to the chemical potential for that substance. And so the biggest change is that this piece is now telling us that we're using the partial pressure of the component, which, if you remember, is equal to the mole fraction of that component times the total pressure. So what does this actually look like? Well, it's going to look a lot like what we've seen before. And so here I'm going to put chemical potential. We're actually going to look at the difference between the chemical potential and the chemical potential at standard state. And then down here, we're going to do it based off of the pressure. And so I'll put markers on 1, 2, 3, 4, 5, and then I'm going to just mark 0 here. And so what happens is the first thing is when our partial pressure is equal to our standard pressure, then that means that our natural log is of 1 bar over 1 bar, which is the natural log of 1, which is equal to 0. And so at that point, we can mark it here, and we see that if this is all 0, then that means that when the pressure of the component is at standard state, so at 1 bar, it equals the chemical potential of that substance at 1 bar. And so this whole part goes away. And so then below 0, this is going to decrease exponentially. And then above this value, it's going to increase until it levels off. And so this really looks a lot like what we saw before with the phases. And so remember that the chemical potential is really telling us about the entropy, right? Because the Gibbs free energy is really telling us about the total entropy of the system. And so this is telling us how likely a reaction is going to occur when the substance is in standard state. So if the pressure is higher, then it gives the substance more of a tendency to react.